Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The mid-20th century witnessed a profound acceleration in the quest to decipher the fundamental architectures of life. Within this fervent, intellectual climate, the 1951 publication in the Proceedings of the National Academy of Sciences titled Atomic Coordinates and Structure Factors for Two Helical Configurations of Polypeptide Chains by Linus Pauling and Robert Corey represents a pivotal moment of crystallization, both literally and figuratively, while its companion papers in the same issue announced the discovery of the alpha helix and gamma helix with broad, descriptive strokes. This specific work functions as the endeavour's quantitative soul. It is a document of immense, unadorned power, deliberately eschewing grand narrative in favour of the severe beauty of precise, testable numbers. This essay will undertake a systematic evaluation of the claims, methodologies, and implications presented within this dense and monumentally significant paper, proceeding through its logical sections to appreciate how it transformed a brilliant chemical intuition into a concrete, verifiable blueprint for molecular biology. The work's genius resides in its directness, providing the cold, hard data that armed the entire field with the tools for experimental confirmation and, ultimately, a new vision of the protein. Section 1. The imperative for quantitative precision. The paper commences with a statement of purpose. It is both remarkably modest and deeply ambitious. The authors posit that the qualitative descriptions of their proposed helical structures, the alpha helix and the gamma helix, require a rigorous quantitative foundation to be of service to the scientific community. The core claim of this introductory section is that a set of precise atomic coordinates is the essential prerequisite for any meaningful comparison between a theoretical model and the empirical data furnished by X-ray diffraction. This assertion established a new standard for rigor in the field. Prevailing models, such as those from William Masperi's group, were often conceptual and lacked the fine-grained detail necessary for direct falsification or validation. Pauling and Corey's opening gambit is to declare that the era of vague structural proposals is over. Their argument is implicitly methodological. They contend that progress depends upon the creation of models so specific that they generate unique, predictable experimental signatures. The mechanism they propose for this is the calculation and publication of two key sets of data for each helix: the atomic coordinates themselves, defining the exact position of every atom in a repeating unit, and the structure factors, which are the calculated amplitudes of the X-ray waves that would be scattered by such a structure. This initial framing reveals a deep understanding of the practical needs of crystallographers, who require such information to interpret their complex diffraction patterns. The intellectual context is one of intense competition, yet the paper's tone is that of a generous, if supremely confident, offering of tools to the entire research community. It is a declaration that their confidence in their models is so complete that they are willing to expose thee to the most stringent possible experimental scrutiny by providing the exact means. Section 2. The architectural blueprint of the alpha helix. The first major section of data presentation focuses on the structure now canonized as the alpha helix. The central claim here is the assertion of a very specific, non-integer helical symmetry. The authors describe a right-handed helix containing 3.6 residue units per turn. This was a radical proposition. Contemporary thinking, influenced by the symmetries observed in classical crystallography, was heavily biased towards structures with integer repeats, such as 2, 3, 4, or 6 units per turn. The claim of 3.6 residues was born from Pauling's relentless insistence on a set of primary chemical principles: the planarity of the peptide bond, the maintenance established bond lengths and angles, and the maximization of hydrogen bonding. The model presented is one where the nitrogen-hydrogen group of each amino acid forms a hydrogen bond with the carbonyl oxygen of the amino acid located 4 residues earlier in the chain, a pattern often designated as I to I+4. The paper then proceeds to list the atomic coordinates for the fundamental atoms of a peptide residue in both cylindrical and orthogonal Cartesian coordinate systems. The provision of these tables of numbers represents the paper's primary evidentiary offering. The coordinates for the alpha carbon, the carbonyl carbon, the amide nitrogen, the carbonyl oxygen, and the beta carbon are meticulously detailed to a precision of thousandths of an angstrom. This act of publication was transformative. It moved the alpha helix from a diagram in a journal to a three-dimensional object that could be built with physical models or, more importantly, computationally placed within the unit cell of a protein crystal. The evaluation of this section must recognize its profound practical utility. By providing size coordinates in a standard orthogonal system, Pauling and Corey gave crystallographers like Max Perutz and John Kendrew a precise search model. They can now ask a direct question of their data: does the diffraction pattern of hemoglobin or alpha-keratin correspond to the pattern that would be produced by this exact atomic arrangement? The intellectual rigor is further demonstrated by their careful definition of the helical parameters, specifying a translational pitch of 1.5 angstroms along the main axis per residue, leading to a full pitch of 5.4 angstroms for each complete turn of the helix. Section 3. The gamma helix as a rigorous alternative. Following the detailed exposition of the alpha helix, the paper presents a complete set of coordinates and parameters for a second, alternative structure, the gamma helix. The inclusion of this model serves a critical intellectual function, showcasing the author's systematic approach. It acts as a self-generated competing hypothesis, demonstrating that their methodology could produce other plausible, hydrogen-bonded helical structures. The central claim for the gamma helix is a different geometry, one characterized by 5.1 residues per turn and a hydrogen bonding pattern connecting residue I to residue I plus 5. It is described as a wider, more open helix with a smaller pitch per residue. The authors present its atomic coordinates with the same meticulous detail afforded to the alpha helix, again providing both cylindrical and orthogonal values. This allows for an equivalent, direct comparison with experimental evidence. However, a close reading of the paper reveals a subtle, internal critique of the second model. While presenting the gamma helix as a sterically permissible structure based on their foundational principles, the author's own data implies a less optimal configuration. The larger central hole within the gamma helix, a consequence of its 5.1 residues per turn geometry, suggests a less efficient packing of atoms. This detail, though unstated as a direct flaw, would have been immediately apparent to any chemist or crystallographer examining the coordinates. In a sense, Pauling and Corey were not only providing the data to test their primary hypothesis, the alpha helix, but also providing the data that would likely disprove their secondary one. This demonstrates an exceptional level of scientific integrity. The gamma helix functions within the paper is a testament to the power of their theoretical framework, which was capable of generating multiple solutions, while also providing the very means to discriminate between them. The subsequent decades of research have shown the alpha helix to be a ubiquitous motif in proteins, while the gamma helix remains a theoretical rarity, validating the subtle cues within Pauling and Corey's own initial presentation. Its inclusion was a masterstroke of rhetoric, cementing their authority by demonstrating that they had explored the landscape of possibilities with unparalleled thoroughness. Section 4. The predictive power of structure factors. The final and perhaps most crucial section of technical presentation involves the calculation of structure factors for both the alpha helix and the gamma helix. The fundamental claim of this section is that the published atomic coordinates can be used to generate a theoretical X-ray diffraction pattern, which can then be directly compared to real experimental patterns. A structure factor is a mathematical description, a complex number representing the amplitude and phase of a wave scattered from a crystal plane. The collection of all structure factors essentially constitutes the raw, processed data of an X-ray crystallography experiment. For Pauling and Corey, to publish calculated structure factors was an act of profound predictive power. They were, in effect, handing the scientific community a finished answer key. The methodology they employed involved using their coordinates to calculate the Fourier transform of the electron density of their proposed helices. This is a mathematically intensive procedure, described in the paper as involving cylindrical structure factors calculated using Bessel functions. The authors detail the intensity distribution along different layer lines of the theoretical diffraction pattern. A key prediction for the alpha helix was the presence of a very strong reflection on the meridian, the central axis of the diffraction pattern, corresponding to a spacing of 1.5 angstroms. This number, derived directly from their model's pitch per residue, became the single most important piece of testable evidence. The paper presents tables of these calculated f-values for various reflections, providing a quantitative signature for each helix. The evaluation of this section highlights the work's function as a direct challenge and an invaluable aid for Max Perutz, who had been struggling to interpret the diffraction patterns from hemoglobin and keratin. This paper was a revelation. He had observed a strong 1.5 angstrom reflection in his data for years but had been unable to account for it with any existing model. Upon reading Pauling and Corey's paper, he immediately recognized its significance. A theoretical prediction precisely matched his empirical, unexplained observation. This moment, an apocryphal tale of science at its best, represents the complete validation of the paper's internal claims. The published structure factors were accurate enough to solve a major experimental puzzle, instantly elevating the alpha helix from a plausible theory to the accepted reality. Section 5. The confluence of theory and biological reality. The concluding paragraphs of the paper serve to connect the abstract world of coordinates and structure factors to the tangible world of fibrous proteins. The authors explicitly state that their calculations for the alpha helix configuration are in good agreement with the X-ray diffraction data for synthetic polypeptides and, more importantly, for alpha-keratin, the protein found in hair and wool. This claim anchors their theoretical exercise in biological substance. They note that the strong meridional reflection at 1.5 angstroms and a strong equatorial reflection corresponding to the side-to-side packing of the helices are prominent features of the keratin pattern. By making this connection, they demonstrate the immediate explanatory power of their model. The paper's final argument is one of unity and simplification. It suggests that this single, elegant helical structure, derived from fundamental chemical principles, could account for the structure of a vast and important class of proteins that had thus far resisted detailed explanation. The evaluation of this concluding section must acknowledge its strategic importance. After pages of dense, technical data, the authors deliver the payoff, explaining what this data means for biology. The reception of this paper, intertwined with its companion pieces, was immediate and electrifying. It provided the intellectual and practical framework that allowed the field of structural biology to move forward with unprecedented speed. The work of John Kendrew on myoglobin and Max Perutz on hemoglobin in the following years would have been immensely more difficult, perhaps impossible on the same timescale, without the precise search model provided in this paper. The coordinates and structure factors were the essential bridge that connected the chemical logic of the peptide bond to the biological function of complex proteins. It established a new paradigm where theoretical model building, grounded in chemical first principles and expressed in the language of precise, falsifiable coordinates, became a central driver of experimental discovery. In conclusion, Pauling and Corey's 1951 paper on atomic coordinates and structure factors is an academic work of profound and enduring significance, a masterpiece of quantitative science. Its claims, evaluated section by section, reveal a deliberate and brilliant strategy. The work begins by establishing a new standard of rigor, moves to provide the exact, detailed blueprint for the alpha helix, validates its own methodology by presenting a competing gamma helix model, and culminates in the ultimate predictive act of publishing theoretical experimental results. Each table of numbers, each coordinate, and each calculated structure factor served to transform a beautiful hypothesis into a working tool. The paper possesses a unique intellectual weight. It is a quiet, technical document that resounded like a thunderclap through the laboratories of the world. It armed researchers with the precise information needed to see the patterns in their own data, solving long-standing puzzles and opening the door to the golden age of structural biology. The work's ultimate legacy lies in its demonstration that the complex architecture of life could be understood and, more importantly, predicted through the uncompromising application of fundamental chemical principles and the courageous publication of specific, testable data. It is a monument to the power of precision.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.